the last class, we were discussing the Michelson interferometer. The Michelson interferometer, as I told you, works by the division of amplitude. So, we have an extended source from which the incident light falls on a beam splitter, and the beam splitter divides a single wave front into two wave fronts, one which is reflected and another which is transmitted. So, the amplitude of the incident wave front is divided to produce two wave fronts. These two wave fronts traverse two different paths along the two different arms of the interferometer. So, this is one arm of the interferometer, the transmitted wave travels along this arm, comes back and then is reflected into the telescope. The reflected wave propagates along this arm, it goes up and then is reflected back, passes through and again is collected in the telescope. So, we have two images of the source of the ground glass plate which are produced, and the waves from these two images interfere with each other. So, we considered a particular point on the ground glass plate. S1 is the image of this point. In the first, S1 is the point corresponding to this point in the first image, S2 is the point in the second image. The waves which will be emitted from these two images will be coherent because they are images of the same point on the source, and these two waves will be focused to the same point by the telescope, and you will get a bright or dark point over here. So, the intensity here will be bright or dark depending on the phase difference between these two waves. The phase difference between these two waves is 2d cos theta. The phase difference between these two waves arises because of the path difference, and this is 2d cos theta. So, you have to multiply it by 2 pi divided by lambda to get the phase difference. There is also an extra phase difference of pi because one of the waves undergoes internal reflection while the other one undergoes external reflection. So, finally, we had this expression for the phase difference between the two waves, and you will get a dark fringe if this condition is satisfied. So, you will get a dark fringe, the intensity will be dark, will be very small if this condition is satisfied, where d is the difference in the arm lengths, theta is the angle at which you are looking, and m is an integer. So, if 2d cos theta, the path difference, is equal to m lambda, you get a dark fringe. If it is m plus half lambda, you get a bright fringe. So, this was the fringe condition which we had discussed in the last class, and I had also told you that the fringe pattern is going to be circular. This is because the whole thing is symmetric around this axis. So, a point over here at the same angle theta is going to have the same intensity as the point over here, and not only that, all points which make an angle theta with this axis are going to have the same intensity. So, the fringes are going to be circular, and you will have dark and bright, a pattern of dark and bright fringes which are circular, which looks like this. We then had calculated the order of the central fringe. When the central fringe is dark, the order of the central fringe is 2d by lambda, where d is the separation between the two arm lengths, the difference between the two arm lengths. We then had calculated the fringe spacing, which is the angle between the central dark spot and the first dark ring. Calling this angle theta, we had found that theta is lambda by d. So, we found that the fringe spacing gets smaller as the separation between the two arms is increased, and if the two arms are at exactly the same separation, the central dark spot grows till it fills the entire field of view. So, the whole field of view is dark when the two arms are exactly of the same length. As you increase the length, the fringe spacing gets smaller and smaller, and for very large lengths the fringes are going to be very close together. So, for a very large difference in the lengths. The next thing that we had considered in the last class was what happens to the fringe of a particular order m as you increase the difference in the arm lengths. So, we had followed the evolution of the fringe of a particular order, a dark fringe of a particular order. So, you have a dark fringe of a particular order at the center if the difference in the arm lengths d satisfies this relation that 2 d by lambda is an integer m. So, if 2 d by lambda is an integer m, you will get a dark fringe of order m at the center. Now, as you move one of the mirrors increasing d, this particular fringe, so the mth order fringe will move outwards, as you can see here. So, it will move out and you will get a new fringe. So, this fringe is now of a order which is higher than this because d has increased. So, m also has to increase. So, the central fringe now, when you increase d, the central fringe is now of one order higher, and the fringe which was at the center earlier has now moved to a larger angle. If you increase the distance even further, the fringe will move out to even larger angle, and finally, it will move out of the field of view, and new fringes have appeared in the center. Fringes of higher order have appeared at the center. So, you can use this to measure the wavelength of light. We had discussed this in some detail in the last class. What you have to do is you have to move one of the mirrors. So, what you do is you move one of the mirrors so that you get, let us say, 1000 new fringes at the center, and you measure the distance that you have to move one of the mirrors so that you get 1000 new fringes in the center. This distance we call delta d, and we had seen that delta d for 1000 new fringes, delta d is going to be 500 into the wavelength. So, even if the wavelength is small, delta d is something that you could measure, and from this, from measuring delta d, the distance that you have to move one of the mirrors, you can determine the value of the wavelength. Now, today we will start off discussing another very interesting application of the Michelson interferometer. So, today we are going to consider a situation where we are using some light to do the Michelson interferometer in the Michelson interferometer. So, we have the fringes produced by a certain light of a certain wavelength, but suppose that the light which is incident is such that it is composed of two spectral lines which are very close together. Such a situation is not very uncommon. For example, the sodium vapor lamp which we use quite commonly in the lab, also used as to illuminate the streets. The light from the sodium vapor lamp has got two spectral lines. So, sodium has got two lines which are very close together, which are produced in the sodium vapor lamp. These two lines are at 589.0 nanometers and 589.6 nanometers. So, the light which you get from the sodium vapor lamp has two spectral lines which are very close together. The question is, suppose I have some radiation, some light which is coming from a source, and I would like to find out first, is it one wavelength or is it two wavelengths or multiple, and if there are two wavelengths, then what is the difference in the wavelength between these two wavelengths. Now, if the difference is quite large, you could send the light through a prism. The refractive index of the glass in the prism depends on the wavelength. So, the prism will disperse the light, and the two different wavelengths would come out at two different angles. So, the situation would be as follows. We know that the glass has a different refractive index for different wavelengths. So, if you send in light which has got two wavelengths in it, lambda 1 and lambda 2, the two wavelengths would come out at different angles, even though they are incident at the same angle. The light which comes in has these two wavelengths, the light would get dispersed and the two different wavelengths would come out differently, and you could you could determine the fact that there are two different wavelengths in here, not one. But this will work only if the separation between these two wavelengths is quite large. If the separation between these two wavelengths is not very large, is very small, then the difference in angle between this and this would be very small and you would not be able to measure it. So, I have given you one example, the example of sodium. Sodium produces two spectral lines, one at 589 nanometers and one at 589.6 nanometers. So, they are only 0.6 nanometers apart. The question is, how would you determine, if I did not know the difference in wavelengths to start with, how would I measure it? And Michelson interferometer is a technique by which you could measure the difference in wavelengths. So, the situation which we are going to consider here is as follows. We have light which has got two wavelengths, two spectral lines in it, one at lambda 1, another at lambda 1 plus delta lambda. So, the light which is coming into the Michelson interferometer has got two different wavelengths, lambda 1 and lambda 1 plus delta lambda, and we are going to assume that delta lambda is very small, much smaller than lambda 1. And the problem is, how do we measure this small difference in the wavelength? The wavelength itself, as we have seen, is quite small. It is a difficult task to measure it, but you can do it using the Michelson interferometer. Now, the question is that you have two light of two wavelengths which are coming in, and the difference in these wavelengths is itself again much smaller than the wavelength, and how can you measure this using the Michelson interferometer? So, the way you go about doing this is as follows. You first, so the first point to note is, before I go into the method by which you do it, the point which you should notice that if you have light of two different wavelengths in your coming into your Michelson interferometer, they are going to produce their individual fringe patterns, and the fringe patterns which are produced by these two wavelengths are going to be different, because the wavelengths are different. Okay. Now, suppose I adjust the difference in the arm lengths d so that the fringe patterns of both the wavelengths coincide. So, let me consider a particular situation here. So, we have these two wavelengths, lambda 1 and lambda 1 plus delta lambda. Suppose I adjust my interferometer so that this wavelength lambda 1 produces a dark spot at the center. So, the condition that has to be satisfied is 2d. I have to adjust the difference in the two arm lengths so that 2d is equal to m1 lambda 1, where m1 is an integer. If I adjust d so that this condition is satisfied, the fringe pattern produced by this wavelength lambda 1 will have a dark spot at the center. Now, if I choose d in such a way so that the wavelength lambda 1 plus delta lambda also has a dark spot in the center, then there will be another integer m2 such that m2 into lambda 1 plus delta lambda, the other wavelength, is also equal to 2d. So, there will be two integers m1 and m2 such that this condition, both these conditions are satisfied, that 2d is equal to m1 lambda, 2d is also equal to m2 lambda plus delta lambda. If I can find two integers, so if I can find a d, a separation in the arm lengths, so that both these conditions are satisfied, then both the fringe patterns will have a dark spot at the center, right. And if this condition is satisfied, we could also ask the question, which is the fringe, is the order of this fringe or this fringe, which one is going to be larger? So, since this wavelength is larger, the order of this fringe has to be smaller, because the product of this and this is the same. So, from here we can also see that if this condition is satisfied, M2 should be less than M1. So, both these wavelengths have a dark spot at the center. This is of a lower order, this is of a higher order. So, such a condition is referred to as, so if the fringes of both, if the fringe patterns of both the wavelengths coincide, this situation is referred to as concordance. So, the picture over here shows us a situation where the two fringe patterns are in concordance, but this is not the situation that we had discussed. This is exactly the opposite situation where we have a bright spot in the center for both of them. But so, bright spot and dark spot can be handled in exactly the same way. You have to just add a factor of half over here and here. Okay. So, this shows you concordance. So, the fringe pattern corresponding to lambda 1, this is the fringe pattern corresponding to lambda 1. The fringe pattern corresponding to lambda 1 and this is the fringe pattern corresponding to lambda 1 plus delta lambda, both of these coincide. So, if you can set up your interferometer so that you have concordance, then the resulting interference pattern in the central region is going to be the sum of this interference pattern and this interference pattern. The bright spots are going to add up. So, the brightness over here is going to increase, the dark rings are also going to add up and this dark ring is going to be darker, is going to be remain dark. So, the contrast, the dark spot is, the dark ring is going to be as dark as this one or this one, but the brighter ring, the intensity is going to get doubled. So, the contrast between the dark fringe and the bright fringe is going to become twice, because you have now got two fringes. So, when you have concordance, the fringe pattern is very sharp in the sense that it is very distinct. The fringe pattern is very distinct, the contrast in the fringe pattern is very high. So, this is what happens when you have concordance, when the fringe pattern of the two wavelengths coincide. Now, a point which you should note over here, a point which may arise in your mind is as follows. Can the two fringe patterns coincide everywhere in the field of view? Well, you should, if you go back to the condition for the fringe condition, let me go back to the fringe condition. So, what is the condition for the formation of fringes? So, the condition for the formation of a dark fringe is 2d cos theta should be equal to m lambda. Now, you can see that if lambda is different, if I have lambda 1 and lambda 1 plus delta lambda, the two fringe patterns cannot coincide everywhere. As you increase theta, they will not coincide anymore, but you can ensure, the point to note here is that you can ensure that they coincide in some central region. The fringe patterns coincide in the central of the field of view. So, we are not really concerned whether they coincide or not in the outer parts of the field of view. What we are interested in is that the fringe pattern should coincide at the center of the field of view, and this is going to happen if this condition over here is satisfied. If M1 and if I can find integers M1 and M2 so that this condition is satisfied, then you are going to have a situation where the fringe pattern coincides at the center of the field of view. Now, let us ask the question that I start from concordance and I slowly move one of the mirrors, so as to increase the separation between the two arm lengths. So, what I do is I start from concordance. So, I have a particular value of d and I increase I move one of the mirrors so as to make the separation between the two arm lengths d plus delta d. And look at the intensity at the center. So, at the center we look at the intensity at the center. So, the point to note is if I increase the value of d to d plus delta d, the value of M1 is also going to increase, the value of M2 is also going to increase if I restrict my attention to the center. So, center is cos theta equal to 0 at the center, the order of the central fringe is going to increase for both m1 and m2. So, for the wavelength lambda 1, I will have m1 plus delta m1. For the wavelength lambda plus delta lambda, lambda 1 plus delta lambda, I am going to have m2 plus delta m2. Now, let us ask the question, how much is delta m1? And it is quite clear from here that delta m1, so if I increase the separation in the two arm lengths, m1 will increase by an amount which is twice the separation by lambda 1. So, what we see is that m1, the order of the central fringe for lambda 1 is going to go up by 2 delta d by lambda 1. The order of the central fringe for the wavelength lambda plus lambda 1 plus delta lambda is going to go up by delta m2, which is 2d divided by lambda 1 plus delta lambda. This will be 2 delta d. So, the point to note over here is that if I move one of the mirrors so as to increase the separation in the lengths of the two arms, I move one of the mirrors by an amount delta d. For the wavelength lambda 1, the order of the central fringe increases by a certain amount. For the wavelength lambda 1 plus delta lambda, for the second wavelength, the order of the central fringe increases by a different amount. So, initially both the wavelengths had a dark fringe at the center, but as I change the difference in the arm length, they both no longer remain dark, and there is a difference in phase. So, there is a difference in the order of the fringes in between the two wavelengths. So, the fringe pattern is now no longer in concordance. Okay. So, this is going to be increased by a certain amount, this is going to increase by a certain amount, and both the fringes at the center do not have the same intensity because they are of different orders. And you can also note that delta m2 is less than delta m1, right, because the wavelength here is larger. So, if I move one of the mirrors by a fixed amount delta d, the change in this is less than the change in this. Now, suppose I keep on increasing delta d, so that the difference in this and the difference between these two is such that delta m2 is equal to delta m1 minus half. So, what have we done? We have moved one of the mirrors. This is going to change the order of the central fringe for the two wavelengths, and we move the mirror so that the change in the order of the fringe for one wavelength and the change in the order of the fringe for the other wavelength, they differ by half. Now, when the difference is half, remember, so m1 was an integer and m1 has gone to m1 plus delta m1, m2 was also an integer, this has gone to m2 plus delta m1 minus half. So, the point to note over here is that in this situation what you are going to have is that the bright fringes of one of the wavelengths are going to coincide with the dark fringes of the other wavelength, because if this is an integer and I make delta m1 an integer, then I will have a dark spot here, dark ring corresponding to this, and I will have a bright ring corresponding to this, because this is an integer to start with and this is also an integer and this is a factor of half. So, when I have a half integer multiple of lambda, I get a bright ring. That is what we had seen earlier. So, if this is dark, this is going to be bright, or if this is dark, this is going to be bright. So, if I move delta d, if I move one of the mirrors, so that the difference between delta m1 and delta m2 is half integer, we are going to have a situation where the bright rings of one wavelength coincide with the dark rings of the other wavelength. Such a situation is what is referred to as discordance. So, let me now show you what we mean by discordance. So, this is the situation referred to as discordance. Notice that for one of the wavelengths lambda, so for one of the wavelengths we have a dark spot at the center, for the other wavelength we have a bright spot at the center. Now, if you superpose, so if this is lambda 1 and this is lambda 1 plus delta lambda, we have a bright spot at the center for lambda 1, we have a dark spot at the center for lambda 1 plus delta lambda. If I superpose these two, the bright spot here is going to fall on the dark spot here, the dark spot here, the dark ring over here is going to fall on the bright ring over here, and the resultant pattern that I have, which is the superposition of these two, is going to be more or less uniformly illuminated. So, the fringe pattern as a consequence is not going to be very bright, is not going to be very distinguishable, and the fringes have essentially washed out. So, in discordance the fringe pattern gets washed out. So, what we see is that I start from a situation where the two fringe patterns coincide. We have concordance, the fringe pattern is very intense, the contrast is very high. I move one of the mirrors, slowly the fringe pattern will get washed out. Now, if I keep on moving it even further, the order of these fringes, so if I keep on moving the mirror even further, so that delta d goes up. So, delta d, I keep on increasing delta d, I will first reach a situation where these two numbers differ by half, and then I keep on increasing delta d even further, then I will reach a situation where these two numbers differ by an integer, right. So, if I move delta d sufficiently, if I move one of the mirrors sufficiently far away, so that delta d is sufficiently large, so that delta m2, the changes in the two orders of the two fringes differ by 1, right. So, delta m2 has to be less than delta m1, this we have already seen from here, and if I increase delta d so that these two numbers differ by 1, which is the condition, this condition, under this condition the bright fringes of one of the wavelength are again going to coincide with the bright fringes of the other wavelength. So, when this condition is satisfied, so let me look at the full expression. So, this condition essentially means that 2 d plus delta d is equal to m1 plus delta m1 lambda 1, this is also equal to m2 plus delta m1 minus 1 lambda 1 plus delta lambda. So, if I change delta d so that the order by which this fringe changes is one more than the order by which this fringe changes, we are back to a situation where we have concordance, because the order of the two fringe systems exactly differs by 1, and if two fringe, so in the situation where I have a dark spot for lambda 1, I will also have a dark spot for lambda 1 plus delta lambda. So, if this condition is satisfied, the two fringe patterns are again in concordance. So, if we can go from one concordance to another, we know that delta m2 will be delta m1 minus 1. Now, we can use this condition. So, we know that at the second concordance this has to be satisfied, at the first concordance this has to be satisfied. We have gone from this situation to this situation. Now, we could subtract this equation from this equation and see what it gives us. So, if I subtract this equation from this equation, what we get, let me write that down here. So, if I do the little bit of algebra, what I will get is 2 delta D is equal to delta m1 into lambda 1, and lambda 2 into lambda 1 plus delta lambda gets cancelled out. This is also equal to delta m1 minus 1 into lambda 1 plus delta lambda. So, let us now see what are the consequences of this. The first consequence of this is that delta m1 is equal to 2 delta D by lambda 1, which we have already worked out earlier. Now, let us see what this tells us. Let us see what this part of the expression tells us. So, let me just focus on this, and when I equate this with this, the term delta m1 lambda 1 delta m1 lambda 1 cancels out. So, what this gives me, what this gives me is over here, let me write it down. What it gives me is delta m1 minus 1 into delta lambda is equal to lambda 1. So, I have just rearranged the terms over here after having cancelled out this term delta m1 into lambda 1, delta m1 into lambda 1 from both sides. This is what I get, and this we could write this as 2 delta D by lambda 1, this is delta m1, is equal to lambda 1 by delta lambda plus 1. Okay. And right at the start, we had assumed that the light which comes into the interferometer has two components, one with wavelength lambda 1, another with wavelength lambda 1 plus delta lambda, where delta lambda is much smaller than lambda 1. So, if I use this assumption, then you see that this ratio lambda 1 by delta lambda 1 is much greater than 1. So, we can forget about this term 1 over here, and what this tells us is that delta lambda is equal to lambda 1 square by 2 delta D. So, this is how you can determine the difference in the wavelengths of the two light of the two lines which you have in your light, two spectral lines. Okay. So, let me again go through these steps, having finished this little bit of algebra. The basic point is that you adjust your interferometer so that you have concordance, the two fringe patterns coincide. Next, you move one of the mirrors so that you go from concordance to disturbance, discordance. If you go into discordance, the fringe pattern which was very bright earlier will now get washed away, it will become very hazy. Keep on moving the mirror until you reach another concordance, fringe pattern again becomes bright. So, if you move one of the mirrors, the fringe pattern starts from a very bright situation, becomes hazy, and again becomes very bright again. Measure the distance that you have to move the mirror to go from one concordance to the next. This distance we call delta D. Okay. So, you determine this distance experimentally. You also determine the wavelength of the light experimentally by the method which we had discussed earlier. So, since these two wavelengths are very close, you can determine the average wavelength by using the method which we had determined, which we had discussed earlier, count the number of fringes, etc. So, you know the value of lambda 1, you know the value of delta D, and lambda 1 square by 2 delta d gives us the difference in the two wavelengths, right. So, so this tells us how we can measure the difference in the intensity in the wavelength of two very close spectral lines in your light. Okay. Another point which I should also mention, that suppose I give you certain light, a light source, and ask you the question, does this light source have one wavelength, is it one spectral line, or is it two spectral lines? If so, then what is the difference in wavelength? So, the first thing that you would have to do there is, then you would have to adjust the interferometer so that you get very intense fringes. Now, if there is only one spectral line, then what you would see is that as I move one of the mirrors, the fringe pattern would remain as it is. It would get, there would be newer and newer fringes coming in, but there would be no very great difference in the intensity. But if instead, if I found that as I move one of the mirrors, the intensity of the fringe pattern gets diminished, the fringe pattern is washed away, and then if I move it further, it again becomes bright, this immediately tells me that there are two different wavelengths, not one. And then I can use the technique which I have just discussed to determine the difference in these two wavelengths. So, this is a very interesting application of the Michelson interferometer. So, Michelson interferometer is essentially a very useful technique for measuring the wavelength of light and determining the differences in wavelength if there are two spectral lines in your light. Now, let me also next move on to other very interesting applications of the Michelson interferometer. Before going into that, let me show you how this how the lengths of Michelson interferometers has progressed over time. So, in 1881, Michelson did this Michelson interferometer experiment using a interferometer where the arm lengths were 1.2 meters. Then there is this very interesting experiment by Michelson and Morley done in 1887, which used an interferometer of length 11 with arms of length 11 meters. This experiment was very interesting, and you may be aware of the very great outcome of this experiment. This experiment, Michelson and Morley experiment, they use a Michelson interferometer. This experiment showed us that the speed of light does not change. Let me explain to you what we mean by this. If we have let us say we have a ball going with speed u in this direction, and there is a car going with speed v in the same direction, then if I am sitting on the car, I will see that the speed of the ball is u minus v. So, this is the law of addition of velocities, and it's this is a key the fact that velocities add up goes by the name of the Galilean theory of relativity. Nothing happens to time, but the velocity adds up, the law of addition of velocities. And the question is, does this also hold for light? And there is no reason why you would not expect it to also hold for light. But Michelson and Morley, they showed that such law of addition of velocities does not hold for light, and this fact that it does not hold for light requires us to revise our whole idea of how to go from one inertial frame to a moving inertial frame. It requires us to abandon this Galilean principle of relativity, Galilean ideas of relativity, where you have the laws of addition of velocity. And it was finally Einstein's theory of special relativity which could really put this thing together, the fact that you have to how to go from one inertial frame to another, maintaining the fact, incorporating the fact that the speed of light does not change. It is an observed fact which was established by Michelson and Morley in their experiment, that the speed of light does not change even if we move. Okay. After that, there were Michelson interferometer experiments with consecutively longer and longer arm lengths. Let me quickly from here jump right into the present times. At present, there is a very large Michelson interferometer experiment going on. The arm lengths of this particular Michelson interferometer experiment are quite large. The arm lengths are 4 kilometers in length, and this picture shows you this particular Michelson interferometer. So, this Michelson interferometer is this is an experiment called LIGO, LIGO, Laser Interferometric Gravitational Wave Observatory, and this shows you a picture of LIGO. It is a Michelson interferometer which has got 2 arms, as you can see over here, as we have studied, and the arm lengths are 4 kilometers, much larger than the arm lengths you see over here, 20 meters, 21 meters, etc. Now, what is LIGO all about? So, LIGO is a joint project mainly involving the it's a joint project mainly involving the California Institute of Technology and the Massachusetts Institute of Technology, Caltech and MIT, and some other American universities. It's an American project funded by various American sources, including the American government, and there are 2 such experiments being conducted in the USA, one at a place called Hanford and another at a place called Livingston, both in the United States of America. And both these experiments are Michelson interferometers with arm lengths of 4 meters, as you can see here. These Michelson interferometer arms are vacuum chambers. So, these enormous vacuum tubes, 2 enormous vacuum tubes, and you have so you have let me I will go into what it does now. Before going into what it does, so what is the purpose of let me go a little bit, tell you a little bit about the motivation for building such an enormous interferometer. So, to understand the motivation, to get some idea of this motivation, we have to take a little look at gravitation. So, we will take a little look at gravity. Now, I am sure all of us here know Newton's the laws of gravity as they were proposed by Newton, and what Newton proposed was that there is a gravitational force exerted by massive objects. So, all massive objects exert a gravitational force, and the gravitational force is also experienced by all massive objects. So, all massive objects exert a gravitational force and also exert gravitational forces, and the gravitational force between 2 massive objects, one of mass m1, another of mass m2, is F is equal to g m1 m2 by r square. This is what Newton's law of gravity predicts, and the gravitational force is attractive. It will cause these 2 objects to come together. Now, we have a few lectures ago discussed the same kind of a situation, but in the context of charges. If I have 2 charges Q1 and Q2, Coulomb had we see that these charges exert forces on each other, and Coulomb had proposed a law governing these forces, which has been experimentally verified, and the law is exactly similar to this, except that you have to use the charges instead of the masses. Now, when discussing Coulomb's law, we had seen that there are certain problems with Coulomb's laws, and we have to replace this. The Coulomb's laws are not exactly correct, and there are modifications which arise, and these modifications incorporate 2 things. I mean, one of the main things which is incorporated is the fact that no signal can propagate instantaneously, and Maxwell's theory gives the correct equation, the correct for the results for the electric field produced by charges, and once you incorporate those corrections, you get a new phenomena which is electromagnetic radiation. We have already discussed this, and we saw that electromagnetic radiation arises when a charged particle accelerates. And there we discussed the situation where we have an oscillating dipole. We have a combination of a positive and negative charge, and we found that if the dipole moment, if there is a second so for electricity, for electromagnetism, we found that if there is a dipole and if there is a second derivative of the dipole, which is equivalent to saying that one of the charges accelerates, you have a part of the electric field which falls as 1 by r, which we refer to as radiation. This carries away energy from the oscillating dipole, and we have an electromagnetic wave which carries away this energy. The electric field, so the electromagnetic wave is a disturbance in the electric field which propagates as, and it falls off as 1 by r as you go away from the dipole. Now let us look at Newton's law of gravity. You see that Newton's law of gravity is exactly similar to Coulomb's law, and it has the same problem, that it does not incorporate the fact that it takes a finite time for signals to propagate. The gravitational force on this would change instantaneously if I were to move this mass. So it should be quite clear that the Newton's laws of gravity, that this particular law, force law for gravity, is not the final story. As far as gravitation is concerned, the final story as it stands now was proposed by Einstein. So you have Einstein's theory of general relativity, which is the correct theory, which is believed to be the correct theory for gravity. In Einstein's theory of general relativity, gravity manifests itself. So gravity is a manifestation of the curvature of space-time. So in Einstein's theory of general relativity, massive objects produce a curvature in space-time, and gravity, what we call gravity, is a manifestation of this curvature of space-time. Now what is crucial over here for our discussion is the following, that exactly analogous to a situation where for charged particle we had a dipole. So for charged particle we had a dipole. If a dipole oscillates, or if I have the second derivative of a dipole, then you have radiation, electromagnetic radiation, which is a disturbance in the electric field which propagates and falls as 1 by r. Exactly analogous to this, now in the gravity, the source of gravity is mass. If you have a mass distribution, and if you go to the center of mass of this mass distribution, then the dipole moment is 0. That is because for charges you have two opposite charges, but for mass there is no opposite mass. All masses are positive, either positive or 0. So if you are dealing with mass, the question of a dipole moment does not arise, but you could have a quadrupole moment. So if you have a mass distribution and the mass distribution has a quadrupole moment q, and if there is a second derivative of the quadrupole moment, so if these masses are accelerating relative to one another, so you have a second, if you have a quadrupole of which has a derivative, second derivative, in this situation you have a phenomena called gravitational radiation or a gravitational wave. This is just analogous to an electromagnetic wave, except that now the disturbance is in the gravitational field, not in the electric field, but there is a disturbance in the gravitational field which propagates. and it falls off as 1 by r as you move away from the source. A disturbance in the gravitational field is also a disturbance in the curvature of the space-time in Einstein's theory of general relativity. So, let me again recapitulate what I have told you. In the Einstein's theory of gravity, gravity is a manifestation of the curvature of space-time. Now, very similar to the electromagnetic radiation, in this Einstein theory of gravity, if you have a quadrupole and if the quadrupole changes, that is, if it has a second derivative, you will produce disturbances in the gravitational field which propagate like a wave, and it is these disturbances that we refer to as a gravitational wave. It is a time dependent disturbance in the gravitational field which is also propagating, and such disturbances are produced when you have a second derivative of the quadrupole moment. So, you could have, for example, wave my hands like this, there will be a change in my quadrupole moment, but the gravitational waves produced by this change are going to be negligible. But there are situations, astrophysical situations, where we have stars. So, if you have two very massive stars in close orbit, the mass of a star like our sun is 2 into 10 to the power 30 kgs, and you could have very massive stars which are maybe 10 times larger than this. So, if you have two such stars going around in an orbit, then the quadrupole moment of this system will have a second derivative. So, such a system is going to emit copious amounts of gravitational waves, and such a system loses energy and angular momentum through the emission of gravitational waves. So, the orbit is going to shrink, and these two stars shown over here are going to slowly come closer together, and if they come closer together, the angular frequency of this orbital motion is going to increase. We had seen for the dipole radiation in electromagnetism that the intensity of the radiation, the total power emitted, goes as omega to the power 4 into the dipole moment, amplitude of the dipole moment square. So, you will have something very similar over here for gravitational radiation. Here again, if the angular frequency goes up, the total power is going to increase, and if the amplitude of the quadrupole moment goes up, again the amplitude is going to increase. So, as if you have two very massive objects like two very massive stars, and if they go around in a circular orbit, they will lose energy through gravitational radiation, they will get into smaller and smaller orbits which will be faster, and you are going to get more and more gravitational waves coming out. The gravitational wave that comes out is a time dependent disturbance in the gravitational field that propagates. So, when the gravitational wave from a distant star is incident upon a Michelson interferometer like this, the gravitational acceleration on these two mirrors in the Michelson interferometer is going to experience, the gravitational acceleration on this mirror is going to be disturbed, and it is going to be a time dependent disturbance in the gravitational acceleration. So, this particular mirror is going to do vibrations like this, and this mirror is also going to do vibrations like this. It so happens that in gravitational waves, the oscillations produced in the two mirrors are out of phase. So, this mirror is going to come inwards, this mirror is going to go out, and then it is going to reverse. So, this mirror is going to come in, this mirror is going to go out, and so this is the effect of gravitational waves, which if they are incident on this Michelson interferometer, it is going to make the mirrors oscillate, and these oscillations of the mirror are going to produce shifts in the fringe pattern which you will see over here. So, if you can detect these shifts in the fringe pattern, the shift in the fringe pattern is going to tell us that a gravitational wave has passed through. So, the main problem over here is that the displacements of the mirror which are produced by gravitational waves, the strains which are predicted from various sources of gravitational waves are extremely small, and in order to detect, it is a big technological challenge to detect these small strains produced by gravitational waves. And these enormous Michelson interferometer experiments have been built with the purpose of detecting these time varying strains which will be produced if a gravitational wave passes through the interferometer. People who work on in this area, they know the kind of signal you would expect if a gravitational wave passed through, and they could then tell you that they have techniques by which they can differentiate between disturbances produced by gravitational waves and other disturbances, and that's what they are trying to do. They are trying to detect gravitational waves. There has not been a positive detection as yet, but the work still goes on. The main problem is that the strains are extremely small, and for a fixed value of the strain, the shift in the length which is produced by a fixed value of the strain is the strain into the length of the arm. So the method to increase the displacement of the mirror is to increase the length of the arm, because the strain is delta L by L, which is why such an huge amount of effort has gone in to build a Michelson interferometer with arms which are 4 kilometers long. And now there is an ongoing effort which to have a Michelson interferometer in space, a gravitational wave detector in space. The whole Michelson interferometer, the mirrors, the source, everything is going to be orbiting in space, so you can have really long arms. So for the same amount of strain, you will have a larger displacement. Remember that the Michelson interferometer measures the phase change which occurs between the two arm lengths, and the phase change is 2 pi delta L by lambda, and the phase change manifests itself as a change in the fringe pattern. So the larger the delta L, the more is going to be the change in the fringe pattern, and it is going to be easier to detect the gravitational waves. So here I have tried to give, in the last part of this lecture, I have tried to give you an idea of one very important application of Michelson interferometers. It is which is in the area of detection of gravitational waves. The detection of gravitational waves is very important for two main reasons. One is that it would be an independent verification of Einstein's theory of relativity. A direct detection would be a very important verification of Einstein's theory of relativity. There are other indirect detections of gravitational waves, but a direct detection would go a long way towards verifying Einstein's theory of relativity. Another very interesting thing is that all astronomical observations till date have largely been based on the electromagnetic radiation. There are some based on neutrinos from the sun, for example, but gravitational waves would open a new window into astronomy, and that is why there is a large amount of interest in detecting gravitational waves using these Michelson interferometers. So let us stop on Michelson interferometers here, and we shall continue on a different topic in tomorrow's lecture.